where sigma x is referred to as standard deviation. Or sigma square is referred to as variance. Okay. Then AX is referred to as mean of the random variable. Is it okay? Then you use MATLAB. Are you familiar with MATLAB, please? One of you please respond. Shiva Datta. Are you familiar with
Yes, sir.
MATLAB?
No, sir.
Good. No, okay. Naveen, is there anyone in the class who is familiar with MATLAB? Bhumika. Bhumika is familiar with MATLAB? Shashank, Nagasai, Karthik, Dasari, Sai, Dheeraj. Okay. See, NITW um, is providing MATLAB, right? Um, so you log into the website and see for MATLAB, you can download free of cost. So what I suggest is everyone should download the MATLAB package, and there are number of packages. Okay, first you download the basic thing, then based on requirement, I think you have to download signal processing tool. Okay, see the tool needed and download. After downloading, the advantage of that package is, suppose I have an expression of this kind, okay, which I am putting a tick mark. First you identify what is the variable. What is the variable now? X. X is the independent variable. By variable, what I mean is independent variable. Okay. So now what is the value to be given to the mean? You define what is the value of the mean. Okay. Then what is the value of sigma x? You define, or sigma squared x. You define. Once you define, then write an instruction to plot. Plot fx of x versus x. Okay. If you are good at C programming also, you can plot, right? Only thing is you have to use library functions, right? So use either C plus or C or learn MATLAB, but you plot this function fx of x as a function of x. When you plot fx of x as a function of x, what are the important things you can observe? When x equal to ax, what is the value of this density function? Just substitute x equal to ax in this expression. When x equal to ax, okay, e power 0 we get. That is, the value of the density function at x equal to ax is simply 1 by 2 pi sigma x square under. That is the maximum value of the density function, and it happens at small x equal to a suffix x. That's why the term ax is referred to as mean of the density function. Is it fine? Now you consider the value of fx of x at other values of small x on either side of ax. Now you consider the value of x equal to sigma x plus ax, the value of density function at, okay, ax minus sigma x. In other words, on either side of ax mean value, I am considering a spacing of sigma x units. When I substitute small x equal to ax minus or plus sigma x in this equation. What is that I get? 1 by 2 pi sigma square under root exponential. The argument for this exponential term becomes minus half. Is it fine? Just substitute x equal to ax plus or minus sigma x. Okay, ax goes away. Simply plus or minus sigma x remains. Square you take. So what is the expression I get? 1 by 2 pi sigma x square e power minus half. Just you see what is the value for e power minus half. It comes out to be 0.607 if I am right. Okay, 0.607. So what is the value of the density function? Okay, at x equal to ax plus or minus sigma x. It is 0.607 times 1 by square root of 2 pi sigma square. Like that, you compute the value of the density function at x equal to ax plus or minus 2 sigma x. Like that, at distinct values of x, you compute the value. If you compute the value, you will get a curve of this type. Okay, something like this. So I will redraw the curve. So around ax, you have the peak amplitude, and on either side of that, the density function decreases like this. It is an even function around ax. Please remember. Okay. And sigma x is defined to be standard deviation, and we define sigma x as the spacing from the mean x equal to ax plus sigma x or x equal to ax minus sigma x, at which the function takes a value of 0.607 times 1 by square root of 2 by sigma x square. That is how we plot the curve. Then to verify whether the given expression is a true probability density function or not. So what is the check we need to perform? Verify whether fx of x is a true probability density function. So PDF we use frequently to signify that the probability density function is being considered. The formula is write down the density function as the argument integrand, then dx equal to 1. Okay. If it is a true density function, since we are not sure, let us not put equal to 1. Then you evaluate this integral. Put x equal minus ax by whatever possible substitutions you make, okay, or then if evaluate this integral, it becomes 1. Any questions in this, please? Can you do this evaluation? That is one thing. Then so this is being used frequently. So this is a constant. This can be taken out. Then What is the next step? E power minus, I can write u square, right? U square. What is dx? From this, dx becomes square root of 2 sigma, square root of 2 times sigma x du. So I need to write the same thing. 1 by pi sigma x square under root integral e power minus u square u du. Because I have u is coming or dx, no, okay, this is not there. Is it okay? Square root of du. Sigma x is there, but sigma x is there. Dx is called s here, right? Same thing, while substitution is being carried out, I made a mistake. So u will not be there. So when you perform this integration, it should yield 1. Okay. Any sigma x is to be removed, right? 2 is to be removed. Okay. This comes out to be root pi. 1 by pi, 1 by root pi times root pi. Any questions? Square root. Yes, this is right on. So let me erase the extra things. This is not there. Then here also sigma x is there. 2 root 2 sigma x. 2 root 2 sigma x. So 1 by root pi. So now expressions are fine. So from this, what I conclude is, I conclude that the given density function is a valid probability density function. Implies that 1 by 2 pi sigma square under root is a valid probability density function. That is how we need to evaluate whether the given density function is a valid probability density function or not. Next thing is, I need to compute what is the distribution function corresponding to this density function. By definition, the distribution function is given as the area under the density function up to certain value of x. So if you recollect the basic properties, minus infinity to x, then what are the components in the integrand? Fx of xi dxi. Okay. So this is what I have to use now. So in this example, fx of x equal to the density function I need to write down. So what are the components within the integrand? Exponential term should be there. How do we show the values taken by the independent variable? I am showing that by xi minus, in place of x I write xi whole square by. What is the reason for replacing x by xi? The reason is the limits are to be taken as minus infinity to x. So if I put the independent variable within the integrand also as x, then I will not be able to distinguish between limits of integration and the independent variable. That's why I have changed the independent variable to xi, a new variable. Okay? And the upper limit for the integration is small x. By definition, the distribution function fx of x is probability that the random variable x takes a value less than or equal to small x. So this is the value under consideration. That value should appear as upper limit in the integration. Is it okay? Now we need to simplify the expression. Okay. As shown earlier. Okay. Next thing is, let the mean value of the random variable be 0. Ax equal to 0. When Ax equal to 0, another assumption we make is the variance of the random variable is 1. Variance or standard deviation. Okay. If sigma x equal to 1, sigma square is also 1. Under these conditions, how does the expression for the distribution function appear? In place of sigma square, we put 1. Okay. 1 by 2 pi. 1 by 2 pi under root, because sigma square is 1. Within the integral sign, what terms do I get? Minus xi square by 2 d xi. Okay. What are the limits now? Minus infinity to x. The idea of this notation is, when I evaluate the integral, okay, when I perform this integration and replace xi by small x limits, the resulting quantity is a function of small x. Now the distribution function is represented as simply f of x. So how do we relate fx of x and f of x? Fx of x is a general expression and f of x is specific case for which values of ax and for which value of sigma x. When ax equal to 0, sigma x equal to 1. That is the difference between fx of x and f of x. Both are distribution functions. Functions computed up to small x. Okay. Now the next question is, I want to evaluate what is f of minus x. So by definition, how do I write this expression? Since we are considering a Gaussian random variable, okay, with zero mean and unit variance, what are the limits? Minus infinity to minus x. So let us plot what is f of x and what is f of minus x. Okay. So how do we plot the distribution function for both the cases? So, okay, we are considering zero mean, unit variance, Gaussian random, something like this. Say x is a positive value. Suppose x is here. My x is here. So area under this distribution function till this. Fine. What is minus x? Minus x will be here. Minus x. So on the right hand side, it is the area under the density function up to that. Now I want to relate f of x and f of minus x. How do I get this area? Or how do I get this total area? What I do is, I will take the whole area under the density function, total area under the density function, and I will subtract from that, okay, from that this area I will subtract. Okay. So total area under the density function fx of x, total area minus area under the density function psi please up to x. What is the total area under the density function? 1. What is the area up to small x? It is f of x. Okay. What is this difference? When I subtract from this figure, it is area under the density function from x to infinity. Is it okay? When I say area under the density function from x to infinity, it is same as, because it is even function, right? It is same as area under the density function from minus infinity to minus x. So 1 minus f of x is simply f of minus x. Is it clear, please? If you have questions, please ask me. I am stopping here. Let me check. Shivadatta, any questions, please? Did you follow what I have put
No,
on the board?
yes,
Yes?
no doubt, sir.
Okay, then Pranay Teja,
Yes, sir.
is it clear?
Yes, sir.
Is this the first time you are listening to this concept or you know already?
Sir, some part I know, sir. Some part.
Hmm. Some part you know. In which subject did you come across this? Naveen, Shashank.
Oh, yes, sir.
Who responded, please?
Sir, Seshank.
Shashank. Did you come across this concept earlier?
Uh, as far as I know, no, sir.
No. This is the first time you are listening.
Yes, sir.
So is it clear?
Yes, sir.
Sarath Chandra,
Sir,
the concept is clear.
sir, can you
So
explain the range?
explain what topic?
The minus infinity to
Oh,
infinity and minus infinity to x. Why is it like that?
yes, I will explain. Okay. Okay. Now I will repeat the figures again because showing the same figure will not help, right? From here I will put. So what I am doing is I want to relate f of x, f of minus x. Okay. This is my aim. Okay. How do I show f of x? For the same density function, I want to show f of x and f of minus x. X is somewhere here. F of x means it is area under the density function up to and including x. Okay, it is the area. F of minus x means area under the density function, okay, up to minus infinity to minus x. These two are to be related. So what I do is I will find out whole area under the density function. From that total area, what I do is I will subtract the area up to x. So what area is left over for me? This area. So the area that is left over is this much. See, this figure is from this, what I conclude is, because density function is even function of x, whether you take area under the density function from x onwards to infinity or from minus infinity to x minus x, it is same. These two areas are same because of even symmetry. And when you see different figures, figure B, figure C, okay, figure D, figure E. Now you compare figure B and E, B and E. Just compare figure B and E. They are same. What is figure B? It is f of minus x. Figure B is f of minus x. How did I get figure B? By subtracting 1 and fx of x. Is it clear?
Yes, sir.
So 1 minus f of x, I did actually. I got f of minus x. This is how we concluded this statement. I hope things are clear, right? Any
Yes.
questions further, please? Okay, if there are no questions, the other thing I need to do is another notation. I'm trying to get a different notation. Now, let me write down the expression for fx of x. When I am trying to put the expression for fx of x, there is no assumption on the values of ax and sigma square. Okay, that means I need to write down uh, the variables for mean, variables for the variance or standard deviation. Standard deviation is simply sigma x, variance is sigma square. Okay, so the integrand contains the terms. Okay, I need to accommodate, right? So what I am writing is right. Only thing is I have to write down in a compact place, right? Minus xi minus ax whole square by 2 sigma square dx d xi. Okay. Now the independent variable is xi. When we substitute the limits, it should result in x. Okay. Fine. Now let me use the substitution. Let xi minus ax by root sigma x. Root is not required, right? Simply sigma x equal to, let me take it as u. When I use that, d xi becomes sigma x times du. Okay. When you substitute this, the terms become minus u square by 2, okay, minus u square by 2 d xi. In that place, you can write sigma x du. Okay. Then simply I can write it as 1 by 2 pi under root. What are the limits, please? Limits are to be interchanged, modified, right? So let me change the limits. So when xi equal to x, the upper limit simply becomes x minus ax by sigma x. Okay. X minus ax by sigma x minus u square by 2, simply du. Okay. Now you just see the terms in the integrand and the scaling factor for the integrand. So from that expression, what I say is, it is as though I have considered a zero mean and unit variance random variable. Is it true? What is this? It is a Gaussian density function with zero mean and unit variance. Sigma square equal to 1. Earlier, we have represented this integral by, this is nothing but f of, what is the argument we wrote earlier? Is simply x, because the upper limit is x. Now the upper limit is x minus ax by sigma x. That is the difference. Is it okay? So these are different ways of representing the Gaussian density function. So a Gaussian density function can be represented by its density function, by the probability distribution function. A Gaussian density function with arbitrary mean value and variance can be represented in terms of a Gaussian density distribution function with zero mean and unit variance. And in the textbook, a few examples are being worked out. Two examples are being worked out. Okay. After I cover the topics, I will try to discuss. These are the two examples to be gone through. Then there is one more function that is defined with reference to Gaussian density function. That is Q function. We say it is a Q function. By definition, this Q function is area under zero mean and unit variance random variable. Okay. So let me write down the area. See, it is area. So integration zero mean and unit variance. So the expression for the corresponding Gaussian density function is given by, is it fine? These. What are the limits? Area under the Gaussian density function. But what are the limits? I did not speak out. Limits are from x to infinity. Would you appreciate this? Now I have changed the limits. Earlier, whenever I wrote the distribution function f of x, the limits are from minus infinity to x. But when I wrote q of x, for this the limits are from x to infinity. This is very important observation to be noticed. Okay. What does this mean? If I have Gaussian density function with zero mean and unit variance, something like this, the area from x to infinity. This is the area that q of x refers to. Is it okay? Now the question is, how do I relate q of x and f of x? In the earlier discussion, this area is nothing but, what was the argument we have presented? It is
f
nothing
of
but,
minus
please,
f of minus x.
f of minus x. Area under minus infinity to minus x. And how did we represent this? F of minus x. Because the area is from minus infinity to minus x. How did we write f of minus x? It is nothing but 1 minus f of x. Now this new function referred to as q function that has been shown as 1 minus f of x. Is it okay? So, or You can write f of x as 1 minus q of x. So based on this q function, there is one more example being worked out. 2.4-3 in the same chapter. Because they are all being worked out examples, I am not detailing. Okay. Any questions till now, please? If there are no questions, okay, I will go to the textbook content. Okay, these are all the things I have discussed and examples. Yes. This is the Gaussian density function being plotted. When you see the x-axis, it is the independent variable in this case. When x equal to sigma x. Okay. Hope the letters are visible, text is visible. Okay. When the independent variable x takes a value of ax, let me place the cursor. Yes, I hope cursor is visible. When x equal to ax, what is the maximum value of the density function? 1 by square root of 2 pi sigma square x. When you consider a separation of sigma x from ax on either side, the value of the density function becomes 0.607 by square root of 2 pi sigma square. This is the density function. How do I get distribution function? We need to take integration. Is it okay? When you perform integration, the curve we get is shown on the lower side. Is it okay? When you perform derivative of the lower function, distribution function, we get the upper function, right? And in this you see, for distribution function, when small x equal to ax, so where is ax? Along x-axis, in the lower figure, you need to identify ax. What is the value of the distribution function? It is 0.5. Okay. On either side, you consider a spacing of sigma x. By what amount the distribution function falls? 0.5 minus 0.159. By that amount, the distribution function falls. Okay. On higher side, by what amount the distribution function raises? 0.841 minus 0.5. That is the rise. Okay. Any questions? I have a good question, right? Here values are shown with negative signs, right? Did you notice? Are they negative or simply dashed lines? They are dashed lines, so no negative value. Any next? Okay. And just I want to show that I have discussed f of x equal to this expression just now I have given. And f of minus x equal to 1 minus f of x, that is also we have seen. Then this expression also we have seen, fx of x equal to f of x minus ax by sigma x. Here the subscript capital X refers to general density function. Here on the right hand side, capital X refers to the case when we consider zero mean unit variance. This is the problem. And this is another problem. The next thing is yes. approximation for q of x. So this approximation is valid only when A is given by 0.339 and B is given by 5.510. When those two values are chosen in this expression, okay, then q of x is differing from f of x by an amount of 0.27%. That means for the values we compute, the values differ by 0.27%. That means 0.2027. So small difference, right? So what this q of x in this expression says, e power minus x square by 2 by 2 pi under root, right? It is referring to Gaussian density function with 0 mean and variance of 1. It is to be scaled by this quantity. What are the terms in the denominator of this ratio? 1 minus a times x, a times square root of x square plus b. So a and b are to be defined, and x is a independent variable, right? It keeps taking values. Okay, this is another expression example. Yes. Now other distribution and density functions. By this what we mean is, for Gaussian random variable, what values the variable can take? The variable can take values from minus infinity to plus infinity. That means all possible values the random variable can take. It is nothing but the case of continuous random variable. A random variable can take continuous values or discrete values. In case the random variable takes discrete values, there are certain density functions. For example, binomial density function. In the previous class, we have seen how to model an experiment when it has got only two possible outcomes. We have modeled that example by binomial trial, right? Bernoulli trial. Yes. So the same thing we are referring to now. In the previous class, what we have considered was when we consider an experiment that has got only two possible outcomes, uh, the probability of occurrence of one outcome is small p, and the probability of occurrence of the second outcome is, say, 1 minus p. Okay. Why I am searching for this is, I should write down here as fx of x equal to f of. To supplement this, I am looking for the content. Okay. Now, here, okay, let me write down. Yes, we have seen Bernoulli trials, right? Just recollect. So what this trial says, I have an experiment, only two possible outcomes. Okay. The probability of occurrence of one outcome is p. The probability of occurrence of another outcome is 1 minus p. Experiment is repeated n times. Out of n times, say event A should happen k times. When event A has to happen k times, what is the probability of that event happening? For that, what we wrote, p suffix p power k 1 minus p raised to power n minus k. This is the probability of occurrence of that event. But how many such events can happen? This is the number of events that can happen. Okay. What is the total probability of that event happening out of n experiments? This is the total probability. When I want to write down the expression for density function, what I wrote simply, I have added one term, impulse function, and said this is the density function. See, the same thing is listed over here. What it says, P is bounded by 0 and 1. N can take any value. In that case, the binomial density function is given by equation 2.5-1. See the similarity between 2.51 and the expression I have listed in this page. I find both to be same. Is it okay? So out of Bernoulli trials, I have a random variable taking values. That random variable is represented by the density function given by equation 2.5-1. Once we got this expression, I want to verify whether it is a true probability density function or not. Is it true probability density function? What is the formula for us to check whether the given density function is a valid density function or not? Find area under the density function. When I try to find area under the density function, all the terms are to be included, right? N minus k, delta x minus k, n minus k please, dx. Okay. So how do we evaluate this integral? Constants, let us take them out. These are all constants, right? So which term will remain in the integral? In the integrand is simply delta of x minus k dx minus infinity to less infinity. Okay. What is this value, please? Area under the unit impulse function. So when x equal to, this is nothing but this value. When you, what is this each one? It is the probability of occurrence of specific event one time, 0 times. When k equal to 0, let me put down one more step. I am trying to show how to find the or verify how do we verify whether the given random variable is valid density function or not. Given density function is a valid probability density function or not. What values k takes 0 to some upper value, right? So n0 p power 0 1 minus p whole power n plus nc1 p power 1 1 minus p n minus 1 and so on, right? What is this probability? Probability that event A happens 0 times. Event A 0 times. Plus, what is the second term? Probability that event A happens 1 time. Like this, I have sum of so many probabilities. So, sum of all the probabilities is 1. That is how we do. For discrete random variables, this is how we establish that the given random variable is given density function is a valid random variable. The next thing is, how do we plot this density function? I am referring to equation 2.51 from the textbook, and I am trying to plot the density function. What values the random variable takes? Random variable takes only positive values. X equal to 0 is possible, 1 possible, 2. All integer values are possible. Okay. So substitute for what value of n? First we need to define n, say n equal to 50. When you fix the value of n, for this value of n equal to 50, so when k equal to 0, what is the value of the density function? K equal to 0 means n is 50, k equal to 0, p power 0, 1 minus p raised to power 50. So we need to say the value of p also, right? So specify value of p. Then 50 C1, p power 1, 1 minus p raised to power 49. Put these values in this graph, okay? Have this value say p naught, p1. So p naught is here, p1 is here. So in the textbook, the problem is solved. Okay, this plot is available. Right? That is how we need to plot the density function. Okay, how do we get distribution function? We need to integrate the density function. When you consider the integration, we get step function. Integral of this delta of x minus k dx up to specific value of x. So we get we got this we have already seen. So in place of delta of x, we need to write u of x. That is how we get the density function, right? Sorry, distribution function. See, figure 2.51 illustrates binomial density and any questions, please? Binomial distribution and density functions. Okay. So where is figure 2.51? It is here. This is that figure, and see the description of this figure 2.51. Okay. For n equal to 6, small p equal to 0.25. For n equal to 6, p equal to 0.25. That means x will have values up to 6, 0 to 6. For each value of x, okay, the values are computed and plotted along y-axis. Now, how do we get the distribution function? By integrating the density function. When I integrate density function, what I need to do? See the strength of this impulse in the density function at x equal to 0. The strength of this impulse is 0.1780. When I integrate, wherever there is a density function impulse, I need to show unit step function of that height. So at x equal to 0, in the distribution function, in the figure that is shown below, I need to show an step function of height 0.1780. Okay. Then at x equal to 1, there is an impulse of strength 0.3560. When I integrate this, I will get unit step of height 0.3560. That step height of 0.356 is to be added to the previous unit step height. So 0.3560 plus 0.780. That gives 0.5340. I hope that discussion is clear. Okay. So there is an impulse at x equal to 0, say an impulse at x equal to say 1. This is density function. How do I get step function from this distribution function f(x) of x? This is say okay a1, this is a2. So at x equal to 0, I should show step height of a0 units. This is a0. At x equal to 1, I should show step of height a1. This is a1. Okay. But I need to add a0 to a1. So this step height will increase. This is how the value. What is this value? This is a0 plus a1. That is how we get the density function. Is it okay? At each value of x, I need to add the contribution from the previous things. So if you prepare every day, it is like distribution function. You are adding something to what is already known. On any day, if you don't prepare, what does it mean? You are not contributing to the process of learning. So whenever I see the distribution function, for me it appears that every day I should have some improvement over my previous day capabilities. That is how I look at distribution function. When I see the density function, I feel that I should act at the appropriate time. Okay. Whenever there is a need, I need to respond. Whenever there is a question, I should explain. Any other questions, please? That is about the binomial density function. From the density function, we can infer many things. Look at the x-axis. By looking at the x-axis, we will understand what values the random variable takes. The random variable takes only discrete values 0, 1, 2, 3, 4, 5, 6. Only 7 values it takes. Okay. By looking at the distribution function, what inferences do we get? We don't know what values the random variable x takes. It can be a continuous random variable or discrete random. Because the steps are shown, staircase waveform, we can infer that it is a discrete random variable being considered. The maximum value of distribution function is 1. That means you have included all possible outcomes. Okay. And for every value of x, there is small rise. That means every event happens with certain probability, however small it is. Okay. Any questions, please? If there are no questions, let me stop here. Any questions from your side?
No, sir.
Okay, thank you. I am closing the session. See, tomorrow is anyway, there is no class tomorrow. So what I plan is I missed the class on 13th because of festival. Okay, I will upload one asynchronous class, and probably next week I may be on leave. I will inform you. Okay, through your CR. So I will upload one asynchronous class or two asynchronous classes, and I will ask you to go through them. Okay. And when we meet, I will be clarifying on those classes. Is it fine? Tomorrow I will upload one asynchronous
Yes,
class. Okay. One more class also I will upload maybe before 2nd of February. Okay. If I am on leave, I will inform you well in advance. Okay. Okay. Thank you for staying with me. So I am signing off.